In this video segment, we will take a look at two simple systems and derive the equations that govern those systems. The first system is a very simple chemical reaction where propane combustion is considered, right? So the reaction, as we know, is that propane burns with oxygen to give carbon dioxide and water, right? So hydrocarbon burning combustion results in carbon dioxide and water. Now, the equation, right, can be written, it's an irreversible reaction. The equation can be written in this particular way. W moles of C3H8 combines with X moles of O2 to give Y moles of CO2 and Z moles of H2O. So this is the equation, right? So the unknowns here as listed in the problem are W, X, Y, and Z. So there are four unknowns in the problem. And we know that, the mass balance is to be preserved. So as we have learned to balance equation in school or in, early years of the college, so we are trying to balance this equation by finding out the appropriate values of W, X, Y, and Z. Now, what we can do is we can write elemental balances, right? Molar balances, if you like, for the elements, right? So we will understand that W plus X is not going to be equal to Y plus Z. Moles are not conserved, right? If you're looking in that particular way. But moles of carbon should balance on both sides. Moles of H, hydrogen atom, should balance on both sides of the equation. Similarly, moles of oxygen atoms should balance on both sides of the equation, right? So elemental species will conserve in terms of moles as well, all right? So with that in mind, let's write down the equations for the three species that we have there, three elemental species, namely carbon, H, hydrogen, and O, oxygen. So when we write the equation for carbon, on the left hand side, we have three carbon atoms in 1 mole of propane, and therefore in W moles of propane, you will have 3 W moles of C. So that is the C on the left hand side of the equation. On the right hand side, C appears in carbon dioxide only. So 1 mole of carbon dioxide contains 1 mole of C. Therefore, Y moles of carbon dioxide will contain Y uh, moles of C. Therefore, we have this equation 3W equals Y. So the moles of carbon on the left hand side of the equation, this is the moles of carbon on the right hand side of the equation. Therefore, we have 3W is equal to Y, or 3W minus Y is equal to 0. For hydrogen, we have 8 times W. That should equal 2 times Z. So you have 8W is equal to 2Z, or 8W minus 2Z is equal to 0. When you write the balance for O, so you have 2 times X on the left hand side, right? So on the left hand side we have 2X. On the right hand side, if you count the number of O's, you have 2 times Y, right? So it's going to be equal to 2Y plus Z times 1 plus Z. So this is the O balance, right? So 2X is equal to 2Y plus Z, and therefore we can write 2X minus 2Y minus Z is equal to 0. So we have these three equations. And this is all we can get because we have balanced all the elemental species on the left hand side and the right hand side. So here we have three independent equations, but we have four symbols: W, X, Y, and Z. So what we need to do here is we need to specify at least one of the symbols. For example, if I specify W, then this system, right, let's say I specify W to be equal to 1. In which case, we will still have three equations, but now the unknowns will only be X, Y, and Z, which we can find out from these three equations. Or we can specify Y, or we can specify X, or we can specify Z. One of the symbols has to be specified, And using that value for that particular symbol, we can find out the other three unknowns, right? So if I specify W to be equal to 1, I'm working with a basis of calculation to be 1 mole of propane. If I specify W to be 1, I'm saying the basis for my calculations is going to be 1 mole of propane. And then I can find out how much moles of oxygen is required for that, and how many moles of carbon dioxide and how many moles of water it will produce, right? So if you remember in the stoichiometry course or in chemical engineering principles course, we are always asked to write a statement at the beginning saying what is going to be the basis for the calculation. Basically, it helps that because many, if you have a different value of W, let's say we choose W is equal to 2, the value of X, the value of Y, and the value of Z has to be multiplied by 2 in order to balance out everything, right? So that is the idea, okay, behind saying, okay, I'm going to fix W to be equal to 1, and then I can find out X, Y, and Z in this particular example. So here is an example, a linear system of equations, but we have 4 symbols but only 3 equations, and therefore the trick or the procedure is to specify one of the symbols and calculate the other symbols, right, unknown symbols, after fixing one of them in this particular case. All right, so this concludes this particular example. Let's next consider a problem that comes from heat transfer. So if you do a course on heat transfer, you will come across this problem at some stage, right? So what we have is, let's say, a rectangular plate of, let's say, 5 centimeters in length and 3 centimeters in width. Thickness is kind of very small, right? The thickness of the plate is small, so you can consider this to be a two-dimensional object. And what you're told is the top side of this rectangular plate is maintained at 0 degrees Celsius. The left side of the plate is maintained at 5 degrees Celsius. The right side of the plate is maintained at 20 degrees Celsius. And the bottom side of the plate is maintained at 10 degrees Celsius using some mechanism. And the idea is to find out the temperature profile inside the plate. So at any point xy, what is going to be the temperature that will be measured at steady state, right? So let's say this plate was stored at 100 degrees Celsius somewhere, and then you bring it suddenly to this environment where the left face is maintained at 5, the right face is maintained at 20, the top face is maintained at 0 degrees Celsius, and the bottom face is maintained at 10 degrees Celsius. So this plate, the temperature of this plate will undergo transients, right? Because it is adjusting from the original temperature distribution to these new boundary conditions that you have set up. So ultimately, this plate will reach a steady state, right? So the temperatures at every point in the plate will reach some temperature and it will remain steady. So the question is, what will be the temperature at any point in this rectangular plate? So to solve this problem, what people normally do is they will break this rectangular object into grids, right? So you have horizontal grids and you have vertical grids, and then we try to compute the temperature at those intersections that you see there. In this case, the grid size in both the dimensions is kept at 1 centimeter. So this is 1 centimeter, this is 1 centimeter, this is 1 centimeter, this is 1 centimeter, and this is 1 centimeter. So equidistant grid. So again, this is 1, this is 1, this is 1. So 1 centimeter is the grid size. So what happens is, if you assume this to be the grid size, then you have these intersecting points which are shown here. There will be 8 intersection points, and the temperatures at those 8 points are as indicated there. So if you choose your grid size to be 0.1 centimeters instead of 1 centimeters, you will have many intersections and you will have many symbols in that particular situation. So the number of unknowns in the problem depends on the grid size that you choose. So if you want accurate results, then you will use a finer grid size, a grid size of size 0.01 centimeters. if you want coarse answers, right, approximate answers will do, then you will use a larger grid size like we have chosen here. So because I'm illustrating this problem for the class, I'm using this grid size of 1 centimeters. But if I were to solve this problem using MATLAB or COMSOL, then I would use a finer grid size to get the finer aspects of this temperature distribution inside this plate. So in any case, for the example that we have chosen, for the geometry of the system that we have chosen, we have these, 8 symbols, T1, T2, T3, all the way till T8. So the idea is, what are the values of T1, T2, T3, T4, T5, T6, T7, and T8? That's the task before us. Now, at this particular point, what would be the temperature? Because I said the top plate is maintained at 0, the right side plate is maintained at 20. So you can say this particular point, if you were to ask, if you're asked what the temperature is at that particular point, you can take the average of 0, which is the temperature of the top side, and the temperature of the right hand side, which is 20, take the average and say this is going to be 10 degrees Celsius. All right, so this will be at 15 because it is going to be the average of 10 and 20. This corner will be at 12 at 7.5, which is the average of 5, which is on the left side, and 10, which is the bottom side of the plate. And this one will be at 2.5 degrees Celsius. Okay, so that's besides the point. Now, what I'm trying to tell you here is that this is the how the problem is set up, right? How the problem is solved by using some concept called grid size or gridding the system, and then kind of that leads to certain points, and you kind of whatever is the property that we are interested in there. In this case, it is a temperature. So we say, well, I want to find out the temperature at these grid junctions, if you like, right, at these points, particular points. So we have identified 8 points because of the way we have done the gridding, right? So we need to find out T1, T2, T3, T4, and till T8. And basically, a simple model which we can derive, but a simple model will be that at each grid point, the temperature is approximately, right, approximately equal to the average of the 4 nearest grid points on the left, right, top, and below. So the temperature T1 is going to be the average of this temperature, this temperature, this temperature, and this temperature. So you look basically at the 4 nearest neighbors, if you like. And then the temperature T1 is going to be the average of 5, 0, T2, and T3 in this particular case. So you take those 4 values, 5, 0, T2, and T3, you average it out, that will be equal to T1. T6, right? T6 will be the average of T4, T8, T5, and value of 10 according to this particular assumption, right? So whether you choose 4 neighboring points or 8 neighboring points, etc., it's up to you. So in this particular case, they say, well, if I take the 4 nearest grid points and I average out the temperatures, I'm going to get the approximate value of the temperature at that particular node. So with that idea, you can write these equations. T1 is going to be the average of these 4 temperatures, as I said, right? T1 is going to be the average of 5, 0, T3, and T2. So that is what is written here. T1 is going to be the average of, so you divide by 4 because it is the average of 4 numbers. So average of these 4 things. So once you do that, you get 4T1 is equal to 0 plus 5 is 5 plus T2 plus T3. And therefore, if you take the unknowns as we normally do to the left hand side, you get 4T1 minus T2 minus T3 is equal to 5, which is what is equation 1. So if you do it for, let's say, T7, if you do it for T7, that means you're looking for this particular point. T7 is going to be the average of 20, 0, T5, and T8. So T7 is going to be equal to 1/4 of 0 plus 20 plus T5 plus T8. So in other words, 4T7 is going to be equal to 20 plus T5 plus T8. Or in other words, 4T7 minus T5 minus T8 is equal to 20. Or in other words, 4T7, minus T5 plus 4T7 minus T8 is equal to 20. So I'm from here to here, what I've just done is I put T5 first and then T7 and then T8, right? So I'm preserving the order of the index, right? From the lower index to the higher index without distorting the equation. So you can develop all these equations. You can develop all these equations. All right. So you have 8 equations in 8 unknowns here. So we have an 8 by 8 system. So you can write out the A matrix and you can write out the B vector, which is going to comprise of these numbers that you see on the right hand side. So that will form the B vector. So you can put it on the form AT is equal to B, where A comes from these coefficients that you see on the left hand side and B comes from the right hand side as we have discussed. T is going to contain 8 elements. T1, T2, T3, T4, T5, T6, T7, T8, the 8 numbers. So this is going to be the vector of unknowns. So we know A, we know B, and therefore we can solve the problem again, right? Using the backslash command or the inv of A times B command. Now we know that for an 8 by 8 system, right? 8 equations, 8 unknowns, you have 64 entries, right? An 8 by 8 matrix will have potentially 64 entries. And what you do is you can also count the number of non-zero elements in this A matrix. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So out of 64, there are only 28 non-zero entries in A. So this is again a sparse system, right? So many of the entries in the A matrix will be zero, as is often the case, right? So this is going to be a sparse system. And on top of that, what we also have is that this A matrix, right, when we do it, we will see this A matrix is going to have what is called a tridiagonal structure. So the main diagonal, right, will be non-zeros. In fact, it will be 4. And then one thing on top, you have something called a super diagonal, which is above the main diagonal. That will comprise of typically numbers like -1. And subdiagonal, which is one below the main diagonal, right? You will have again numbers like -1. So the non-zero entries of A, so this is the A matrix, the non-zero entries of A will be all in the diagonal or in the super diagonal or in the subdiagonal. Other entries will be 0. So these are called banded matrices, right? Or in simple terms, this is a tridiagonal system, tridiagonal, because the non-zero elements are on the main diagonal or on the super diagonal. That means one above the main diagonal and subdiagonal, one below the main diagonal. So these will help us to use some special algorithms to solve for the unknown T, right? Because we can exploit the structure of the A matrix in order to come out with efficient ways of solving the problem. All right. So not all A matrices are the same. Depending on the structure of A, if there is any special structure, people have developed algorithms to solve those systems efficiently. For example, to solve tridiagonal systems, we will see something called the Thomas algorithm later. Okay. So this is the idea. So this problem is from heat transfer, and you can nicely set it up and solve it numerically. Thank you.